Test, test. Okay, Austin, Jair, Roman, y'all see me, hear me, see my screen?
Yes.
Okay.
Yeah.
All right, everyone. So I put up this problem here. Let's go ahead and take a look at it. Here we go. So exam 2 is on Wednesday of next week. Right. So my goal here is to try and get you a review this in the next day or two. All right. That way you can have some idea what to expect. All right. So if you don't see something by like Friday night, email me or text me. I should have something ready to go. All right. The integral that I wanted to start with was integral negative infinity to infinity of x e to the x dx. So this is a problem from the idea from last class, right? So we want to know what's happening here. You know, we have an improper integral, right? We have our limits of integration contain infinity in them, right? So we have both negative infinity and positive infinity. So what's the first thing we need to do? Separate them into two, right? Okay, so let's go from negative infinity to where? 0. We can go anywhere, right? But we'll go 0. It makes the most sense. So negative infinity to 0 of x e to the x dx. And then add to that, let's pick up at 0 and go to infinity. Same integrand, x e to the x dx. Now, both of those are going to have to be done with limits, right? That's the way we do these. So I'm going to have to have two separate limits that I do. So watch the way I write this. For the first one, I'm going to let the limit go as t goes to negative infinity. And then what I'm doing is I'm replacing this negative infinity with a t, right? So it's going to go from t to 0, and then x e to the x dx. That's my first one. Plus now a new limit. Now I could use t again. I could say let t go to positive infinity this time. But just so we don't get confused with letters, right, with variables, I'm just going to call it something else. So I'm going to just do r goes to positive infinity, and then replace that infinity on the integral with r. So 0 to r, x e to the x dx. So what we see in the brackets here, those are now just definite integrals, right? They go from a number to a number. Of course, one of them is a variable, but we treat those just like we did before, which means that we need to find the antiderivative of x e to the x, right? So that's kind of separate work. I think I'll do that down here, just kind of as a separate little problem. I want to find the antiderivative of x e to the x dx. And had anyone figured out how to do this? Integration by parts, right? Was this a homework problem? It seems like it was. No?
Close.
Yeah, it was. Okay, so we go u is x. I thought about putting x squared e to the x here instead as a problem. That would have just required two steps of integration by parts. But to keep it simple, just went ahead and did this. So du is e to the, or dv is e to the x dx. When we fill out the integration by parts table, we'll get a 1 dx here, and the antiderivative of e to the x is itself. So I'm doing integration by parts because when I do it, I'm realizing that if I let this be u, when I take its derivative, it'll become 1. And then that makes the e to the x dx be the dv. When I integrate that, that'll become itself. So I'm kind of foreseeing what voodoo is going to look like, right? Voodoo is going to be that integral, the integral of this, which is just the antiderivative e to the x. So I'm happy about that. So rewriting this becomes, let's see, ultraviolet x e to the x. That's multiplying that u times the v minus the integral, and now the v, which is e to the x, times du, which is dx. Any questions on that? Antiderivative of e to the x is itself plus c. So that would be the good old-fashioned antiderivative, if that's all we had to do, right? That's it. But that needs to be plugged in up here with, or up at the top with our definite integrals. So let's go ahead and take that answer and plug it in here. Okay, so here we go. We have equals the limit. T goes to negative infinity. And then I'll keep the bracket here. It's the antiderivative, which we just found was x e to the x minus e to the x, evaluated from t to 0. And then plus limit r goes to infinity. And then the same thing over here, x e to the x minus e to the x, evaluated from 0 to r, whatever that is. And now we have to plug in, right? Plug in 0, plug in t, and then plug in r, plug in 0. So let's see what happens. So I'm going to have two things here subtracted in this bracket. So when we plug 0 in, right, 0 in for x, it'll kill off this first term, right? 0 times anything is 0. And then we have minus e to the 0, which is 1. So this will give me -1. And then when I plug in t, well, all that does is replaces all the x's with t's. So, and then I add to that the other limit with r going to infinity. And then again, I'll have two things here that are going to need to be subtracted. When I plug in r, it just replaces all the x's with r. So r e to the r minus e to the r. And when I plug in 0, well, we did that earlier. Didn't we get -1? Like that. This all makes sense? No questions? All right, so now, we've got to figure out what's happening here. If t goes to negative infinity, what happens here, right? As t goes to negative infinity. And then on the other one, we got to figure out what happens to r, e to the r minus e to the r, if r goes to positive infinity. All right. So let's just think about this. Maybe I'll do this again. This is kind of like separate work here, I'm trying to fit it all on one page. If I take the limit as t goes to negative infinity of t e to the t minus e to the t, what happens? So think about this. T is getting really big and negative, right? So where does this head to? Where does t go if t is going to negative infinity? Negative infinity, right? That's headed to negative infinity. Times, now careful here, where is that going? Where's e to the t going if you're heading to negative infinity? 0. So the way to understand that is think about the graph of e to the t, right? Or e to the x. It looks like this, right? It's an exponential function. It grows as you go to the right. As you go to the left, it asymptotically approaches 0, doesn't it? That's what e to the x looks like. So e to the t would look the same way. And where are we headed? We're headed to negative infinity, right? So that means we're looking at this graph as you head out to the left, which means it's headed to 0. Yay? Yeah? Yes? So that goes to 0. Let's just keep going. We'll deal with that in a second. Minus, now where does e to the t go? We just said it goes to 0, right? So that's headed to 0. Now, unfortunately for us, I'm gonna erase this. I'm gonna take this to the next page just to get it out of here. So unfortunately for us, when you have negative infinity times 0 in a limit, that is an indeterminate form. That's not 0, right? Because this number is not 0. That number is getting close to 0, and this number is getting very big and negative. So, you know, who wins? So in Cal 1, hopefully you saw how to deal with this indeterminate form. I know in my Cal 1 classes, we use Lhopitals Rule for this. So y'all remember Lhopitals Rule? Mm-hmm. When can you use Lhopitals Rule? What type? It has to be a certain type. When you actually use Lhopitals Rule, the limit has to look a certain way. What does it have to look like? You have to have 0 over 0 or infinity over infinity, right? So maybe we should just recap what L'Hopital is. L'Hopital's rule, it's spelled Lhopitals, okay? L'Hopital's rule says this: if you're taking a limit, doesn't matter what your limit is, okay? And you've got something over something. If that limit goes to 0 over 0, or if it goes to positive or negative infinity over positive or negative infinity, if that happens, okay? So you're taking some limit, you're getting 0 over 0, or you're getting infinity over negative infinity, doesn't matter if they're plus or minus, then whatever that answer is, okay, whatever this answer is equal to the limit, same limit, but instead of the top, you take the derivative of the top and you take the derivative of the bottom. So if this limit exists, it is equal to the limit of the derivative of the top and bottom, not quotient rule. Okay, this is not quotient rule from Cal 1. This is a special rule for limits. So it says that if you get 0 over 0, infinity over infinity, all you need to do is take the derivative of the top, derivative of the bottom, and then do the limit again and hope that it gets better. The problem here is that we don't have 0 over 0 or infinity over infinity, right? We don't have that. We have negative infinity times 0. So you cannot use L'Hopital's rule until you make it look like this. So I know one of my Cal 1 students is going to tell us how to do that. Anytime you see infinity and 0 together like that, what the thing is, drop one of them down. Good. So what you're going to do is you're going to pick one. So look, does everyone agree first that this is not an issue? That goes to 0. Who cares? Okay, that goes 0. It's going to go away. What really matters is what happens here. So I'm going to focus all my attention on that right now. And I'll say it again. If you ever see infinity times 0 in a limit, you're going to take one of the two and drop it to the bottom. Now, in this case, you have a choice. You could drop the t down to the bottom or the e to the t down to the bottom. It's up to you. I don't care. Let's drop the e to the t. Maybe it seems more natural. Well, what do y'all want to do? T or e to the t? I don't care. What would you have done? Yeah, you would have done t. Let's do t then. Okay, so what do I mean by drop it to the bottom? You can't just put the t down there. You have to write it like this, because it has to be the same expression, right? So I'm going to take the e to the t, leave it on top, and I'm going to write the t that used to be out front as 1 over t on the bottom. That's what I mean by drop it. You're really just rewriting it. This t is now 1 over t on the bottom. And do you all agree that if I reciprocated that back up, it would be a t on top? So I really haven't changed the problem. But what I have changed is what the limit looks like. Because if you now take the limit and you ask, where does that go? Well, where did we say that went? E to the t, as t goes to negative infinity, that goes to 0, okay? And then on the bottom, if you look at this, 1 over t, the whole expression, where does that go? If the t is getting really big and the top is 1, right? 1 over a big number, it should head to 0, right? Now it'll be negative, right? It'll be heading to 0 through negative numbers because the top is positive, the bottom is negative, but that doesn't matter. It's headed to 0. So now you have this expression that looks like 0 over 0, right? And so now you can use Lhopitals rule. Okay? So Lhopitals rule, usually when we do Lhopitals rule, we need to indicate that we're doing it. So I believe the textbook puts an H over the equal sign to let everyone know that we're using Lhopitals rule. I've seen different textbooks do it different ways. Me personally, this is just me. I don't know why I do it this way. I put an L and I circle it, and that's just me. You can do an LH, I don't care. Just something to indicate that you're doing something. Okay, you're going to use the rule. So here it comes. I'm using the rule. So I take the derivative of the top, which is itself. And then I take the derivative of the bottom. Okay, 1 over t. That is really t to the negative 1, isn't it? So if you take the derivative of that, you get negative 1 over t squared, or negative 1 t to the negative 2, which is negative 1 over t squared. Understand? Okay, we have a problem. It's the same result. Okay, so if we try it again, we do e to the t, we let t go to negative infinity, the top goes to 0 and the bottom goes to 0 again. And it'll keep doing this because every time we take derivative of the top, it's just going to stay e to the t. And every time we do this, we're just going to get 1, either positive or negative 1 over just a bigger and bigger power of t, which means that it didn't work. Okay. Why? Well, we just happened to drop the wrong thing. Now that's not, I mean, you couldn't have really known that. You have to try it, right? So this didn't work. So we don't give up. We just say, you know, shit. Okay. You don't have to say that, but now I'm like, shit. Okay. I can't do this. So I've got to do it the other way, right? So instead of dropping the t down, and I'll be honest, I would have wanted to drop the t. The t makes the most sense. But if we drop the e to the t instead, think about what the derivative of the top will be, right? Because if we leave the t on top, then we take derivative of that t, it's just going to be 1, right? Understand? So let's redo it here. Okay, I'm going to leave the t on top. Now, when you drop e to the t to the bottom, I'm going to write it as e to the negative t. Is that all right? That's the same as e to the t on top. The reason I like that is because, well, let's see what happens. Let's first check that we can use L'Hopital, okay? If I let t go to negative infinity, the top goes to negative infinity, doesn't it? And the bottom, be real careful here, because we now have e to the negative t. What happens if I put a huge negative number in right here? The two negatives will go together and become positive, right? So this will be e to a huge positive number, which means you're looking at that graph of e out to the right instead of to the left. And where is that going? Up to infinity, right? So that goes to infinity. And now we have infinity over infinity. Doesn't matter if one of them's plus or minus, that doesn't matter. We can use L'Hopital's rule. With me? It's fun or what? Okay, I have to continue and I'm out of room. So I'm just going to take all this to a new page. Any questions at home?
No.
Okay. All right, so now I'm going to use L'Hopital's rules. So I'm going to go ahead and put a L here. And derivative of the top is 1. And on the bottom, be real careful. We know the derivative of e is itself, right? But you have chain rule here. So you have to do derivative e to the negative t is itself, e to the negative t, times the derivative of what was up here, right? Which is negative 1. But just don't forget that negative 1 does pop out there. And now we let t go to negative infinity again. So notice the numerator is just going to stay at 1, right? And then the denominator, again, be careful. You're plugging a negative huge number in here. The double negative will become positive. So you got e to a huge number, which heads off to infinity, doesn't it? Times negative 1. It's headed to negative infinity, isn't it? Okay, what is 1 divided by a huge negative number approaching? 0, right? Fixed on top, big number on the bottom, that ratio gets small. This heads to 0. All right, so it heads to 0. So back here, somewhere over here, remember we were working this problem, we were asking like, what's going on right here with this yellow, right? This goes to 0. Now, what will happen is on a test, a student will do this, they'll work through this, and then they'll just say this goes to 0. And they won't show me any evidence of it. They'll just say it goes to 0. And that's correct, it goes to 0. But without you showing me why, I can't give you credit for that. Maybe you just got lucky, because most of the time you can't just look at this and know that. You have to analyze it carefully. So don't forget that step when you're actually doing these problems, right? That you might have to use Lhopitals. Now, we still have another one to do, right? We still have this one. Okay, so let's go do that one. So now I need to look at the limit. It was as r goes to infinity of r e to the r plus or minus. Was it minus?
-1.
Wait, it's plus right there? Okay. Wait,
Yes,
hold on.
minus.
It's a minus, right? Yeah, it's minus. See that minus right there? Okay, so it's a minus. Okay, so let's look at this. Let's let r go to infinity, right? Be careful here. We're not going to negative infinity this time. We're going to positive infinity. So r is getting huge. This r heads to infinity times, now notice on this one, e to the r, right? This time that's headed to infinity, right? So infinity times infinity. Well, a huge number times a huge number, that's infinite, right? Infinitely large. So we're thinking, okay, infinity, but then this sucks, minus infinity. Infinity minus infinity is not 0. It's an indeterminate form, just like 0 times infinity was indeterminate. 0 over 0 is indeterminate. Infinity over infinity is indeterminate. Infinity minus infinity is also indeterminate. But there is a way to deal with these. Like in the previous one, we dropped 1 down, right? Someone have like kind of the trick or the technique you use when you see infinity minus infinity? Try and factor. Try and factor. So we can factor an e to the r out, right? Let's see what happens. If we pull an e to the r out, we're left with r minus 1, aren't we? Pull an e to the r out of both of these. And now just look at it again. What happens? As r goes to infinity, this goes to infinity. But now we're saying times what? Infinity minus 1, right? Infinity minus 1 is still infinite. Now, is infinity times infinity indeterminate? No. If I tell you I have a huge number and I'm going to multiply it times another huge number, well, that's going to be a huge number. So this is going to infinity. Shoot. Well, what does that mean? Let's go back to the original question. All this work, right? All this work, and now what we can tell you, or what I can tell you, is that this is headed to infinity. So this one right here is -1. I'm taking away nothing. I'm adding to that infinity, and then I'm adding 1. Well, as soon as I see this infinity, it's over, right? That means that this does what? It diverges. It diverges. Because to have convergence, this thing has to go to a number, right? And it's headed to infinity. I was going to give you all a quiz today. I decided not to. It was going to be basically it was going to be like, not a multiple choice. I was going to give you like 3 or 4 different definitions of what divergence meant and have you pick the best answer. So like one of them was going to be like, divergence is when your limit goes to infinity. The other one was going to be divergence is whatever. And then the correct answer would have been divergence is not convergence, right? And that's what we have here. We have not convergence, which means we have divergence. Understand? If one piece of this diverges or goes to infinity or doesn't exist, we're done, okay? So we did all that for nothing really, because, I mean, we know that the area underneath that curve is divergent. Should we look at the graph? Just for fun? Let's just see what the graph of that looks like. It was x e to the x times e raised to the x. Was that it? There's the graph. I think it's obvious from the graph, don't you? That if we're trying to find the area underneath this, that this area under here, this under area to the left of 0 looks like it could possibly be convergent. Maybe it's headed towards 0. Do y'all see that? So this area in here does look like maybe it's a finite number. Maybe, maybe not. But to the right, no way, right? This is growing. That area just keeps growing and growing and growing. So if we would have looked at the graph in the beginning, we would have known this was going to be divergent. Yes? I wonder if changing it, to, what if it was e to the negative x instead? Would that have changed it? To the right now, it looks like it could be finite, right? But to the left, this area is becoming unbounded. So that doesn't work either, huh? Okay. The main point of that problem was Lhopitals. Can you deal with different types of indeterminate forms? So if you need to, in my YouTube playlist, you can go to my Calculus 1 lectures, and it's section, you'll see the lectures I have, what section they are. It says there, I think I do 3.3 and 3.7 on the same day. It's 3.7. So if you want to go back and review Lhopitals, I've got some resources there, okay? All right, we are ready to move on to the next part of this section 6.6. So we're done. I talked about normal distribution last time. We actually proved this formula last time, right? We proved that that was true. Well, let's just recap what this meant, what this was saying again. It said that if you're looking at the integral from 1 to infinity of 1 over x to any power, that it will diverge if p is less than 1 and converge if p is greater than 1. So let's take a look. Let's take a look at that visually here. Let's say if we do just 1 over x to the n, I want to graph this, y equals 1 over x to the n. Let me see. Yeah. And let's only graph this from 1 less than or equal to x less than it. Yeah, just that. So I'm only graphing this function from 1 on, okay? And right now, can y'all see that okay? See if I can make this a little bigger. Okay, right now we're doing 1 over x to the n, and n is 1. Right now, if we did and tried to find the area under this, the answer would be what? Converge or diverge? If n is 1.
Converge.
Sure? Diverge. Diverge. Oh, that could have been a good quiz question today, huh? Does that converge? We did that in class, right? So if the power on the x is 1 and you're looking from 1 to infinity, the area under there diverges. Now, what if I make it x squared? I'm going to change this to step by 1. Yeah. So what if I make it x squared? Picture looks almost the same, right? But that area converges. It converges, which means it's finite. If I do x cubed, finite, 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 if I keep going. Do y'all see what's happening to the picture? It's all about, and we were talking about this at the end of class, right? It's all about how fast this thing drops. If it drops fast enough, then you get convergence. If it doesn't drop fast enough, you get divergence. So here's n was 1, here's n 2. It's just a subtle difference between the two, right? But it makes a big difference in terms of the area underneath that from 1 to infinity. Now, if I try and do something like, well, if n is 0, what if n is 0? You just get a flat line. Does it make sense that that diverges? Yeah. And if I do like negative numbers, well, now your picture is going to start looking different, right? And I think it's obvious from this that that would be infinite area, wouldn't it? So there we go. Now, I want to make sure you're clear with that because I'm going to give you another formula today. It's going to look like this formula, but it's not the same thing. So everyone understands we're going from 1 to infinity here, yes? Okay. All right. Next, the second type of improper integral. The first type was where your limits of integration were infinite, right? Those are easy to see because when you look at them, you'll see the actual infinity up at the top or bottom of the integral sign. The second type is hidden from you. It's something you have to identify when you look at it. So take a look at this function here. Okay, take a look at this. This is the graph of a function. And I want you to notice that if we're just looking between 2 and 5, and we're asking for this area, notice at 2, it appears that the function has a vertical asymptote, right? Which means that the function like goes up and up and up and up and up. As you get closer to 2 from the right side, it goes up and up. So there's like this little sliver of area the whole way up, isn't there? Just like when we went out in the previous problem to the right, it got smaller and smaller. It was like this little sliver of area the whole time. With vertical asymptotes, we run into the same issue. So here, if I wanted to know what the area there was, right? I'm not headed, do y'all see I'm not like letting x go to negative infinity or positive infinity? I'm looking on an actual finite interval, 2 to 5. But I still have this problem in here because of the vertical asymptote. So this second type of improper integral is called an infinite integrand. Now remember, the integrand is the thing in the integral sign, right? The thing that's here, when you look at an integral, right? This right here, the integrand, is the function. So the second type is saying this is when you have your function itself becoming infinite. Vertical asymptote, right? That's what a vertical asymptote is. Your function's taking off to infinity or negative infinity. That's different than the previous type, which is where you had the infinity up in the limits of integration. And it is possible to have both scenarios happening at the same time. But we'll get to that towards the end here. Let's just deal with this one thing at a time here, okay? All right, so how do we handle this? What if we have this situation where we go from one point to another, and then on the right-hand side, it goes up, right? Forever. Or what if we have something like this where we integrate from 1 to, let's say, 3, and somewhere in between 1 and 3, we have a vertical asymptote, right? We can have the vertical asymptote occur at the left side, the right side, somewhere in the middle. It could occur both at the left and right at the same time. And there's all these different scenarios. So how do we deal with these? Well, it's going to be a limit, just like it was before. It's going to be a limit. We're going to have to see what happens as we let something approach something. So I think the best thing to do is just to go to an example. Okay, so I'm going to start with this example here. Integral from 0 to 1 of 1 over x squared. Now be careful, because we have already established what would happen here, right? What would that green answer be? Convergence or divergence? Convergence, right? That is convergence over there, because we have 1 over x to a power. That power is 2. 2 is bigger than 1. As long as it's bigger than 1, you're going to get convergence. But the key is also that we go from 1 to infinity, right? That's when that's true. If we go from 0 to 1, this is no longer on the table. We're not talking about that anymore, all right? So from 0 to 1, the graph of that, let me go back to my graph here. I'm going to go 1 over x squared but this time I'm going to graph it. Only from 0 to 1. Oh boy. There we go. So the red graph is the thing we're looking at. We're no longer looking at the right side of this. So if you look at this and we're trying to find the area, right, underneath this, that's the area all in here. You can see that it's going to keep going, right? So what do you think? What does your instinct tell you? 1 over x squared, right, going out the right side, 1 over x squared going out to the right converged, right, because it dropped fast enough. As we come to the left and go up on that picture, what do you think? Converge, diverge? Let's see. We'll check. Okay. Let's see what happens. So how do we deal with this? Here's the approach. Okay. What you do is you first look at it and realize you have a problem. You have to see the problem first. So what I realize is that if I look at the original integrand as a function, f of x equals 1 over x squared, I have a domain restriction, don't I? The domain on this is everything except x can't be 0, right? You are not allowed to plug 0 into that function. But 0 is on my integral, right? That's a problem. So the way I like to do this is this. I like to draw a number line. I like to put the interval that I'm integrating over. I'm integrating from 0 to 1, right? That's what the integral says. So I'm going to be integrating from here to here. And what I'm asking myself is, do I see any problems in that interval in terms of it conflicting with the domain of the function? Which I do, right, at 0. So I have a problem here at 0, right? This is a problem. So what I'm going to do is I'm going to tweak this integral. I'm going to change this 0 to something like a letter, like t. And then I'm going to approach that 0. Does that make sense? Instead of actually letting it be 0, I'm going to approach it. When we do that, though, look at the interval. If I ask you to approach this 0, there's only one direction you can approach it from, because you're looking between 0 and 1, right? So I can only approach 0 from the right-hand side, which impacts my limit, because my limit, I'm going to replace the 0 with t, but I'm only going to approach that 0 from the right. Okay, so let me write this down. This is now going to become the limit as t approaches 0 from the right. So I put a little plus sign to the top right corner, right, of the 0 to let you know I'm coming in from the right. And I am replacing that 0 with t, and I'm leaving the 1 as a 1 because that's not a problem. Like that. We good? I need the antiderivative. So just remember, this is really x to the -2, right? So if you take the antiderivative of that, you should get -1 over x, -1 over x. We'll let you do that on your own, but trusting that you're kind of becoming a veteran of power rule at this point. This becomes -1 over x evaluated from t to 1. So antiderivative of this is this. I still need to evaluate at the two endpoints here, t and 1. So now I evaluate. Still have not run the limit yet. Okay, if I run if I plug in, start out with 1, I get -1 here when I plug 1 in, and when I plug in t, I just get -1 over t. right? And now I'm ready to let t go to 0. So if I let t go to 0, right there, what happens? Your number on top, -1, right? The bottom is doing what? Getting smaller and smaller and smaller and smaller. What does a fraction do if the numerator stays fixed and the denominator gets small? It's huge, right? It blows up. It basically becomes infinite. Now, the fact that we're only coming in from the right, the only really important aspect of the fact that we're coming in from the right is just that when we're approaching 0 here in this blue, it's always a positive number because we're approaching 0 from the right, which means we're positive, which just means that this is a negative number divided by a really, really, really infinitesimally small positive number, which means your answer is a very, very big negative number, negative infinity. Okay, but at the end of the day, does it converge? Is it going to a number? Not infinity can't count, right? It has to be a fixed, right? So it's not going to a number, like it doesn't head to 5, doesn't head to -10. It's going to infinity, all right? So this does what then? It diverges. See, this goes to negative infinity. At that point, the whole thing diverges. Cruz, you got that? You understand? The difference between going to infinity and a real fixed number now. Infinity is just, it blows up as opposed to a number like the number 5. No? So did it do what you thought it would do? Yeah, okay. So is it the same? Is this doing the same as what it does from 1 to infinity? From 1 to infinity, 1 over x squared converges, right? From 0 to infinity, I'm sorry, from 0 to 1, it diverges, does the opposite, doesn't it? Okay. Then what about this? What did this one do from 1 to infinity? Diverged, right? From 0 to 1, maybe it converges, right? Maybe it converges. Okay, look at the domain of this function, right? I'm going to draw the interval. I do have a problem, right? At 0, I have a domain issue here. So again, just like the previous problem, I can't plug 0 into this, so I'm going to have to approach 0 from the right-hand side. So I'm going to rewrite this as a limit. T is approaching 0 from the right. The new integral goes from t to 1, 1 over x dx. This becomes the limit. T approaches 0 from the right. Antiderivative of 1 over x is natural log of x, evaluated from t to 1. I'm not doing the absolute value on the x because I'm looking between 0 and 1. So I'd only need the absolute value if I was somehow in a negative domain or something. So I don't need to worry about it. Let's go one more step. Okay, we plug in. If we plug in 1, we get natural log of 1. Minus, if we plug in t, we get natural log of t. What is the natural log of 1? 0. Natural log of 1 should be 0. So that's just 0. And now you want to know what the natural log of t is as t heads to 0 from the right. So that means you need to know what the natural log function looks like, right? Remember what the natural log function looks like, I hope. Looks like this. That's ln x. So what happens to this function natural log as I approach 0 from the right? Where's it headed?
Negative
Down
infinity.
to negative infinity, right? Negative infinity. And what do I know then right now? Diverges.
Diverges.
Diverges. I was thought maybe it would converge. Because when we went from 1 to infinity, it diverged, right? So maybe from 0 to 1, it would converge, but it diverged. Okay. Let's do this one. I think I'm going to let you all mess with this one for a minute. I don't know. What do you think? Do you think I should just give you a few minutes just to look at it? Or do you just want me to crank it out? Give you a few minutes? Yeah, I'll give you a few minutes. So is there a problem between 1 and 4? Can't be 4. Okay. That's right. You're going to want to approach from the right. Did you all find that you can't plug 4 in? How did you figure out that you can't plug 4 in? Did you just like visually do it, or did you try and figure out when the denominator is 0? A little bit of both. Yellow, right? You seem very zoned out. Is it okay? Well, then ask questions. I need you to help me help you. Okay. Okay. So with this function, I guess the main part of this second type is that what we're looking for is where the function would have an asymptote. Okay. Which means we want to know where the denominator would become 0. Because if the denominator is 0, that's where you have asymptotes on functions. Generally speaking, you can also have holes, but generally speaking, wherever the denominator is 0, you're going to have something bad happening. So when we look at this, I want to know when this x squared minus 4 x. When will that be 0? That's kind of what I'm asking myself. And so I can factor an x out, right? And I get two solutions, 0 and 4, right? There are two places where we would have this thing be undefined. So I've got to be real careful that my integral does not go through there, but it does, right? My integral, if I look at where I'm integrating from, I'm supposed to go from what, 1 to 4? So I actually have a problem at this second endpoint, right? I don't have a problem anywhere between 1 and 4. I don't have a problem, right? It's only at 4 that I have the issue. Is that clear? Uh-huh.
Is it weird if I think of it like I plug in the 1 to the denominator and it's 1 over 1,
Uh-huh.
and then I say, okay, so it's negative, so it converges, and then with 4 it's 0, so it diverges?
No, because that's not enough. Just because when you plug in 4 and you get 0 on the bottom, is not enough for you to tell me that the area under this graph is divergent. Sorry, not 0, is divergent. That's
Is
not
it
enough.
still an integral?
You could still have a finite answer. Yes.
Let me
You-
reset.
Yeah, you can. If it were that easy, right? Where all you do is just plug in 1 and be like, okay, if you plug in 1, everything's great. Okay, great. If you plug in 4, you get, 0. Oh, it diverges. If it were that simple, that's the way I would teach it. But you have to analyze the entire thing. You have to run the integral. This area could be finite, could be infinite. Unfortunately, that's what we have to do. So don't look at it that way because you get yourself into major issues that way.
Oh, shit.
Yeah. Okay, so you understand so far? We're just identifying we have a problem at 4. So since I have a problem at 4, what I'm going to do is I'm going to set this integral up. And when I set it up, I'm going to replace the 4 with t, and I'm going to approach t from the left because I'm looking between 1 and 4, right? So the only way to get to 4 in that interval is to come in from the left of 4. So let me set this up. I've got a limit as t goes to 4 from the left, so a little negative sign above the 4. And the integral is going to go from 1 to t, and then 1 over x squared minus 4x dx. Another reason that the endpoints, you can't just look at the endpoints, is that it is possible that the problem you have is actually not at the endpoints, but inside. You'll see, I'll do an example.
Oh, like the 0 point.
Like if this integral went from 1 to 6, right? From 1 to 6, you would not have a problem at 1. You would not have a problem at 6. You'd have a problem at 4, wouldn't you? And 4 is between 1 and 6. So you would have to deal with that. I'll do one of those and just not ready. Go ahead. What's your question?
Oh, no, I was thinking that would be like when
Yeah, let's crawl before we walk here. Yeah. All right. So are we good up to this point? So what do we need to do now? We actually have to find the antiderivative of this. How are you going to do that? Who sees it?
Is it partial fractions?
Partial fractions. So you have to see that this is a rational function, that the denominator can be factored. So now we've got this whole new problem here, don't we? I know, it's Cal too. It's just the way it is. I'm only the messenger, okay? All right, I'm only the messenger. I try as best I can to communicate the message, but the message is the message. Yes.
To factor fit there 0, 4.
Yes.
Is there ever going to be a time when there's going to be 2 numbers that we're going to have? Or is it always just going to have 1?
It could happen. It could happen. Theoretically, it won't happen in this class. I wouldn't do that to you, but yeah, you could.
So in that case, I don't know.
Yeah, you would break it up into 2 limits. Yeah. So yes, what if this integral went from 0 to 4? Right? You would have 2 problems, right? So you would have to do 0 to maybe you go, if this went from 0 to 4, maybe you go 0 to 2 and then 2 to 4. And you deal with each one of them with their individual limits. So I think you're catching on to the idea here, that you have to analyze it, figure out what's going on, and then kind of break it up if necessary.
But I think there in your.
Yeah.
A little bit to like, just everything. I have to make steps in my head.
Yeah. Yeah, okay. All right, so I'm going to do partial fractions here. So I'm going to factor the denominator. Maybe looking at it that way helps. Because we do partial fractions, that means what we're going to do is we're going to say, oh, let's just rewrite this 1 over x times x minus 4. Notice I'm not doing an integral right now. Rewrite it as a over x plus b over x minus 4. See, do y'all see what I'm doing here? We've done that. And then we have to figure out what a and b are. So I'm going to move quickly here because, well, time is an issue. Clearing fractions. And I'm going to do the short method. So I'm going to just like plug in something for x to get a, and then plug in something for x again to get b. So what if I let x be 0? If I let x be 0 here, what would happen? You get 1 equals negative 4a. So a would be negative 1/4. I'm not showing this work. I'm just, because we have done this before. Now, if I want to know what b is, I'm going to let x be 4. So if x is 4, it kills this off. 4 here, you get 4b is 1, so b is 1/4. So I realize there might be some, there might be some steps I'm not showing there, but I'm hopeful that you could get to that. And so now this integral becomes integral of negative 1/4 over x plus 1/4 over x minus 4 dx. Okay, that's what this becomes after the partial fractions. And then this should become negative 1/4 natural log absolute value of x plus 1/4 natural log of x minus 4. So all I did there was just kind of ignored the negative 1/4 because it's a constant. And I looked at this as being 1 over x. And I remember that the antiderivative of 1 over x is natural log of x. And then over here, if you ignore the 1/4, that's like 1 over x minus 4. The antiderivative of that is natural log of x minus 4. And then I just pulled the constants out front. So that's my antiderivative. Questions there? Plus c, my general antiderivative. I need that over here, don't I? So now I come back over here. I say, all right, this is the limit. T goes to 4 from the left of the antiderivative, which I just found to be negative 1/4 natural log. I don't need the absolute value because I'm looking between 1 and 4, so I should be fine. You know what? Let's put it just to be safe. Next one plus 1/4 natural log. This one especially, x minus 4 absolute value, evaluated from 1 to t. Now I replace. So I'm going to go ahead and plug things in. So I'll have 2 expressions being subtracted here. Kind of getting tight on room here. I'm actually really getting tight on room. I'm going to move this down because I need more room. All right, so I plug in t first, right? So negative 1/4 natural log absolute value of t plus 1/4 natural log absolute value of t minus 4. And then the other one I get, now I plug in 1, so negative 1/4 natural log of 1 plus natural, 1/4 natural log of absolute value 1 minus 4. See, I need the absolute value there. All of this on the right is just a number, right? Natural log of 1 is 0. This is the natural log of the absolute value of -3. So that's really just natural log of 3. So this becomes 1/4 natural log 3. Y'all with me on that? Being subtracted from this now. Let's plug in, let's let t go to 4. Right? Let t go to 4. So if t goes to 4, we get natural log of 4. Is that okay? Natural log of 4 is okay? And then we plug in 4 here, right? 4 take away 4, shouldn't that be 0? And so we're basically looking at the natural log function as it approaches 0. We just did that the previous problem, didn't we? Goes where? We're approaching 0 though. That's right. So if you replace that with 4, right? Then this whole thing inside is approaching natural log of the absolute value of 0, right? And so the natural log of 0 is undefined because it's got a vertical asymptote. But as you approach from the right because it's absolute value on the 0. So you're always a positive number in there. So where's that headed? Negative infinity. This headed negative infinity. What can we say then? This thing diverges. They're not all going to diverge, of course. So diverges.
So like at the moment when they like diverge or we get like a negative infinity or positive, do we just like stop?
So the question was, once you see an infinity, like, can you stop? Can you be like, it's over? Yes and no. The only danger is this. What if this first one in front of it would have been positive infinity? Then you have infinity minus infinity, don't you? And so that you don't know. So you would have to actually make sure that this doesn't somehow simplify to something where you can use Lhopitals rule to make it turn out to be a number. That would be where you would have an issue. But if this is turning out to be a number, right? Because if we just plug 4 in here, you got natural log of 4 and then negative 1/4 times that, that's just a number, right? This over here is just a number. And so we have a number, take away infinity, take away another number, this thing diverges then. Does that answer your question?
Yeah.
Okay.
If we have 2 infinities like that, then that means we made a mistake somewhere in there.
No, it just means that there might be more that you have to do to analyze it. It would have to be infinity minus infinity. If you had infinity plus infinity, that would be okay. Or if you had negative infinity minus infinity, that would be okay. It's only if you had infinity take away infinity. Then you would have to do something like factor, right? Lhopitals rule, maybe. Yeah, I mean, Cal 2, I mean, it just forces you to have everything in your arsenal, right? Like all your skills, algebra, pre-cal, Cal 1, they all have to be like sharp. The batteries have to be charged, like you have to be ready to go with them. And that's just the inherent difficulty in this class. I mean, here we have a brand new topic, right? And we have to do partial fractions. So if your partial fractions never felt comfortable, then this is going to be hard, right? I'm trying to decide which one I want to do next. Yeah, let's do this one. the other day, I don't know what made me do it. I was thinking about my Cal 2 professor. I was thinking about why was I able to just understand it, you know? And I went back and I looked him up. He teaches at the University of Missouri. And that's not where I took him for Cal 2, but he's a really brilliant Russian professor. And he would go in there, he didn't have any notes with him, he would just go up there and just start writing stuff out. And I don't know what it was, it just all made perfect sense to me. I don't know if it was just the way he did it or what, I've looked back at my notes, and I'm like, I don't know, it just made sense, just worked. I felt like I had more problems in Cal 1 than I did in Cal 2. And in teaching this class for the last 20 years, I've noticed the same thing. It's like, you can never predict the students that are going to do really well with this the first time they see it, and the students that are going to struggle with it. You just can never really tell. So, I mean, in my experience, you can be a really good math student. You can go on to become an engineer, whatever, computer scientist. You may struggle with Cal 2. You might have to take it twice. You might have to take it 3 times. Don't let that discourage you from continuing down the road of, this is just a tough course. It's just tough, all right? But if you stick with it, you'll get through it, right? But it serves you no benefit, all right? There's no benefit in me going, you know what, you tried real hard, you passed. That doesn't help you, because all these skills from Cal 2, you're going to need them for differential equations. You're going to need them for engineering analysis. If you can't do an improper integral in engineering analysis, goodbye. I mean, they just weed you out, right? So you want to be strong in these things to do well later. So, all right. How about this one? Can I make one more comment? Sorry, one more. Okay. So why does it take 4 years to get a degree? Why can't you get a degree in like 1 semester? Why not take, 120 hours or whatever a degree requires now? Why don't you just do that in 1 semester? You can't absorb that much information, right? It's like you don't go, if you're thirsty, you go to the water fountain. You don't go to the fire hydrant, right? And open up the fire hydrant and be like, ah! Like you don't drink out of a fire hydrant, you drink out of a water hose. That's fine. You can only take in some information. Cal 2 is one of those courses where it's so much information and it relies so much on your past that it just, some people have to see it more than once because it's just too much at one time. And there's no shame in that. It's just the way it is. I wish they would break Cal 2 up into 2 classes. So, Cal 3 is even more information. But I think when you get to Cal 3, you're already like hardened. Like Cal 2 has hardened you. So like what you used to think was really like you've learned how to drink faster. It's so Cal 3 doesn't seem as bad as Cal 2. I always hear that Cal 3, oh, it wasn't as bad as Cal 2. It's like, yeah, it's because you know what suffering is now, right? So, okay. So one of the things we have to really start to pay attention to that we really weren't paying attention to at all before is that there could potentially be a problem in here, right? We don't want to just be like, oh, let me just find the antiderivative now and just go on with the problem. I actually have to investigate, is there an issue? So I'm going to draw a number line. By the way, I think this one's going to converge, so it might be worth our time. 3 and 5. Okay. And I'm going to look in here between 3 and 5. Do I have any problems? Well, what's the number that causes the problem here? 4, right? You were going to say 4, right? Yeah. So it's 4, right? Do y'all see that? If I plug 4 in here, division by 0, I've got a problem, right? That's the only place I have a problem though, right? I can plug any other number in, just 4, just not 4. But unfortunately, where's 4? Right in the middle of this thing. Right in the middle. That's why I'm saying you can't just look at both endpoints, because what if there's something happening inside, right? So we have to approach 4. We have to do a limit to approach 4, but we're going to have to come in from both sides, right, Cruz? So that means we're going to have to split into 2 integrals, do 2 limits, and do 2 different analysis of this thing. Okay. What's that saying? Such is life, or thus is, what is it? Such is life. Have y'all heard that before? No? Thus is life, or such is life. So I'm going to do the integral first from 3 to 4 of this. Am I the only one who's heard that before? Such is life, or
C'est la vie.
c'est la vie, yeah. Tis the season. All right, so first thing I'm doing is I'm just rewriting this as the integral that goes from 3 to 4, then 4 to 5. That's just me recognizing we have a problem at 4. Now, on this first integral, if I'm going from 3 to 4, I'm going to replace the 4 with t, and I'm going to approach 4 from which side? The left, because I'm looking between 3 and 4, right? So I'm going to do a left-hand limit on this one. Limit t approaches 4. I hope I'm not discouraging you. I'm not trying to discourage you all. Like, trying to just be honest with everyone, you know? Going from 3 to t, right? Approaching, t is approaching 4 from the left-hand side. That should take care of that kind of left region of 4. And now I'm going to do another limit. And I'm going to go from t to 5. I use t twice. Is that okay with you all? All right. I mean, it's not wrong to do it that way because these are kind of their own problems. I'm not like Mr. Storyteller today, but I think this is important. I was at Discount Tire the other day getting new tires, which sucked because tires are so freaking expensive right now. But I was getting new tires, and this guy came up to me. He's like, "Mr. D," and I'm like, "Yeah," and I kind of recognized him, and I was, you know, he told me his name, and I remembered him, and he had me for Cal 1 and Cal 2 like 8 years ago. And I was like, "What are you up to now?" He's like, "I went to A&M, finished up my mechanical engineering degree. Now I'm working for a company out in Bernie that makes filters for oil rigs, like big old oil rigs. They do the oil filters, like custom made ones and stuff. And he's their project manager. And now he's going back to school for business administration so he can become management, but he went through the whole engineering part. And whenever I have students like that, I always think to myself, like, okay, so you had a student who went to Northwest Vista College, took me for Cal 1, Cal 2, and went on to get a mechanical engineering degree at Texas A&M. That always makes me feel good because my goal is to make sure that you walk out of here with a realistic chance to compete with the people at the major universities, right? I mean, that's the goal. You need to come out of here. There's no sense in me giving you an A in this class and then sending you to slaughter, right? You have to know the information, right? You have to be ready to take that on. So, yeah, okay. Here we go. We need an antiderivative, don't we? God, if that were, okay, so if that were a square root, I don't know, maybe you would be thinking trig sub if that was a square root, but then that's not x squared, right? So what do y'all think here? I don't know. I need to do this. Let's do it on a different page. Doing the indefinite integral. What do y'all see? Y'all see anything? This is a tricky one. I'll admit it. By parts? You think it's gonna be ugly? I think it'll be ugly by parts. And we could try it. Let's just, maybe there's something else that someone sees. It's so hard to teach this part of this class. Like the instinct is so hard to teach. But really, I think it just comes with so much practice and time. Okay, that's good. A lot of you have the same instinct and it's correct. And what's the U sub? X minus 4. There you go. Now, I think it's hard to see maybe initially that it's going to work, but it is the right instinct. So let's go with this. If U is X minus 4, it becomes du is dx, right? 1 dx. And oh, we're going to replace this with u, right? The dx will be replaced with du. So I'm all happy about that. I just need to somehow handle the x.
You solve for it.
Yeah. Oh, I used that same color twice. Yeah, just solve the top equation for x. So take that, solve for x, you get x equals u plus 4. Okay, this is looking very good then. So you get u plus 4 over cube root of u, right? On the bottom, I'm going to write that as u to the 1/3 du. Now what?
Split them up.
Split them up, right? You have two terms on top, one on the bottom. Just split it up into two. U to the 2/3 plus 4u to the negative 1/3. I already did the simplification. U to the first power over u to the 1/3 is u to the 2/3, and then 4 over u to the 1/3, I bring it up. That okay? Power rule. Add 1, right? So correct me if I'm wrong. 3/5 u to the 5/3 plus, okay, when I add 1 to that, I'm going to get 2/3, and then I have to multiply by 3/2. 4 times 3/2 is 6. U to the 2/3 plus C. Now, what's U? Yeah,
X minus 4.
4, good. So we have x minus 4 to the 5/3 plus 6 times x minus 4 to the 2/3 plus C. All right, that's my antiderivative, right? I think I can just come here. So, oh, it was on a different page, wasn't it? Yeah, here's where we were, right? And I stopped and went and found that antiderivative, which I just found to be this. I'm just going to put it here so I can write it. So I have something to reference here. So back to this. We take a limit as t goes to 4 from the left of the antiderivative of this, which is all of that stuff, 3/5 x minus 4 to the 5/3 plus 6 times x minus 4 to the 2/3. Evaluate that from 3 to t plus the next limit, t goes to 4 from the right of the same thing. But this time going from t to 5. We good? Now each of those we have to plug in t, then 3, and then the other one we have to plug in 5 and t and subtract and do all that and then do a limit. Limit t goes to 4 from the left. Oh, okay. Two things here. It's going to be pretty big. I don't know if I'm going to have enough room to do this all in one line. Bless you. All right. So first I plug in t. And when I plug in t, it's basically everything that's there, right? With t's instead of x's. just thinking about this, and I'm kind of thinking ahead here. What's going to happen when I let t go to 4 here? Right, I'm going to let t go to 4. These going to be zeros, aren't they? And they're just going to 0 and 0, and that should be nice. It's all going to go away. I'm not going to get an infinity there. Okay, but I still need to plug in 3. So if I plug in 3, it'll be 3/5. Let me go ahead and plug 3 in here. 3, take away 4, I get -1, raised to the 5/3. Then plus 6, and then -1 to the 2/3. Is that all right, everyone? That's the first one. I still have to do this one, but I'm out of room. So I'm going to go to the next line. Plus, I'll kind of indent it a little bit so you realize it's continuing from the previous line. All right. So 2 things here. I'll plug the 5 in first. Okay, so if I plug in 5, 5 minus 4 is 1, isn't it? And 1 raised to any power, 1 raised to any power should be 1, right? This 5 is going in here. That's a 1. 1 to any power is 1. So I should just get the 3/5 in front. Plus, and then when I do the 5 into here, same thing. 1 to the 2/3 is 1. So I should just get 6. Yes? Then you subtract from that what you get when you plug in t. All right, so 3/5 t minus 4 to the 5/3 plus 6 t minus 4 to the 2/3. All right. Now it's time to let t go to 4. And like I said, it's actually good because when I let t go to 4 here, here, and even in the other one, here and here, all of those approach 0, right? They all go to 0. So this is basically dead, 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 dead. And so what I'm left with is this. Look right here. I have a negative in front of 3/5. Okay, think about this right here. -1 to the 5/3. What does 5/3 really mean? What does the 3 mean?
Cube root.
Cube root. Okay, what's the cube root of 1?
1.
Cube root of, sorry, cube root of -1 is what I meant to say. Cube root of -1 is -1. Now, the 5 means raise that to the 5th power. So what's -1 to the 5th? -1,
-1.
right? So this is really 3/5 times -1. Plus, now the next one, 6, same story, right? Take the cube root of -1, which is -1, but then square it. So 1, right? So 6 times 1. That's this piece. And then we still have plus the next line down here. This was 3/5 plus 6. Let's distribute this negative sign through. So we should get 3/5 minus 6, and then we can do plus 3/5 plus 6. The 6's cancel, and you get 3/5 plus 3/5, which is 6/5. And it converges. Okay. Any questions or need clarification on any of this? Yes.
How did you know to plug in 4?
The limit. Remember what the limit was approaching?
Okay.
The limit's approaching 4, right? So that's why I replaced all the t's with 4s.
Okay.
So I'm just curious here what'll happen. What happens if I go to Wolfram alpha? And let me see, let me make this a little bigger. This math input, what is this? I think this is new. Is this new? Oh, natural language, that's the mathematical language here. Oh, yeah, you can have a little keyboard here now. Oh, is that new? That seems new to me. So what if I want to do the integral? Where do we want to go from? 3 to 5. Do you think it's smart enough to know that there's a discontinuity in the middle there? Do you think? Let's see. So this is going to be x over cube root, right, of x minus 4. So I'm going to raise it to the 1/3 instead of drum roll. Six fifths. Ooh, it had trouble. It had trouble. It did not know how to handle that discontinuity. You'll see that? Interesting. That's surprising. Huh. Okay, so let's try this. What if we go from 0 to 4? What was our answer? Oh, sorry, 3 to 4 is what I meant to say. Shouldn't that just be that first piece? 3/5 minus 6, right? Let's see what it does. What's 3/5 minus 6? Man, it's really having trouble. Okay, what's 3/5 minus 6? No, as a fraction. 27/5, right? Y'all agree? Negative 27/5. Do y'all see that's what it has here? Negative 27/5 and then times this. What is this? This cube root of -1 squared. That's 1. But it's freaking out. It's trying to bring in complex numbers because it's doing some weird algorithm, right? So obviously this is a weakness. I rarely do I find weaknesses in these online programs. This is definitely a weakness, right? Because it's having a lot of trouble with this. So that's our positive 25ths. If we go from 4 to, what was it, 5, right? We should get the other part, which should be the, what was the other part? 6 plus 3/5? 33/5? Oh, it did okay with this one. Interesting. It did okay with that one. That's weird. That's really weird. But what we can definitely say is that it did not have a good time with this one. Right? It did not have a good time with this. Although, wait a minute, hold on. Is that the same answer it had just a second ago? Is that what it had? So maybe this is 3/5. Maybe this is right. Because that's a 1. Right? That's a 1 and then times 9 and then that's 2 and then 2 times that's 6/5. Okay, so yeah, maybe I don't remember it seeing that. I thought it just had this. I'll look back at my video. I really don't, because if I would have seen that initially, I think I would have just said, oh yeah, that's 6/5. But okay, either way, if you're a student or anyone relying on, I mean, this makes you a little bit skeptical, right? Like, can we truly trust this, right? We do, but you have to, at the end of the day, someone who's programming this needs to know what's going on, right? Like, has to be able to come up with the correct algorithm. Okay, let's see what we have left in our notes for this section. Yeah, that's pretty much it. Oh, no, that one right there. How much time do we have? 10 minutes. See if you can do this one in 10 minutes. See what you can do with it in 10 minutes. This will be the end of, our test is on Wednesday, right? A week from today. This will be the final bit of material that will be on the test. All right, so what we talk about next week before the test, what, on Monday, will not be on the test that's on Wednesday. So you're looking at pretty much all the techniques of integration along with improper integrals. What I like to do is I like to give you an improper integral that requires a technique of integration, right? Like partial fractions, or so I'm killing like 8 birds with 1 stone, right? Instead of giving you like 15 problems to do, I give you fewer problems that require more concepts. I'll send you the review. All right. So here's what we'll do, just because we only have like 9 minutes. Never mind. It won't work. It won't work. We don't have enough time. I was going to make it a bonus opportunity, first group done, but I don't think that you'll be able to finish it. So just do it for fun. All right, that's it. At home, you have any questions?
Oh, don't think so.
I'm okay.
Okay. Make sure you all do your homework for this section and then start the review. Otherwise, I think I'm going to end it, start closing up.
So will you email the review?
I will
or-
email the review. Yep.
And is the homework just the odd or is it all?
Well, I think it says to do
Says odd.
odd. Yeah, I mean, it wouldn't hurt you to try the evens. Just that's a lot of problems. So if you want to do the evens to practice after you've done the odds, go for it. Question? Yeah.
Which sections will be on the exam?
Up through 6-6.
So everything, so all of it?
Well, the stuff we covered in the very beginning, like
6.1?
yeah, pretty much like from integration by parts on. So all of chapter 6 pretty much is there.
All of 6?
Yep, all that. Everything you're looking at between exam 1 and 2 on that calendar, everything there.
Okay.
So integration by parts, trig integrals, trig substitution, partial fraction decomposition, definite integrals.
Defining definite intervals?
Yeah, I mean, that's just where we put the numbers on it, right? So once we put the numbers on the integrals, then that changes what it is. Yep. Well, y'all are messing with that problem. I'll see what I have here handy as far as an exam review. Are y'all going to get together and study? Is anyone going to make a study group? No? What's that? Yeah, y'all should. I have some online Cal 2 students that are doing this online, right? So they actually met up this past weekend at a local public library because the campus isn't open. So you can call up a public library and they have meeting rooms and you can reserve them and you can go as a group if you're interested in that. And they have whiteboards. And so they met this past weekend and they told me they were meeting. So I sent them the review for an exam ahead of time because they were at least being proactive. So if I recommend, that would be good, might be good for you all. Let me see here. You get anywhere on it? No? What's wrong? Oh, do you need the problem up there or no? Okay. What is it? Fall. Here's an old review. We can look at this. This is only a year old. If it just looks like it's a bunch of integrals, it's because that's what it is. Bunch of integrals. Okay. Yeah, I mean, if y'all want, we can just look at this and make better use of our time since that problem is going to take more than 5 minutes. I'll send this out to y'all. This looks like it's at least a good starting point. Evaluate these integrals, no instructions in terms of what method to use. So any instinct on the first one?
To be trig sub.
Trig sub,
factor
probably. Basic U sub probably won't work. Yeah, trig sub sounds good. Second one. Same thing,
trig
right?
sub again.
Yeah. So this is a review. So I probably was thinking, oh, I'll just throw 2 trig sub problems on there. Okay. I think 3, 4, and 5 are obvious.
The partial decomposition.
Partial fractions. I mean, I think it's obvious because they're all rational functions. But number 3 is a definite integral. So there are limits of integration here. And this is like that classic problem that I love, which is a linear over quadratic. Question is whether or not this quadratic is reducible or not. If it's reducible or factorable, then you can use partial fraction decomposition. If it's not reducible, then you're going to use either the method I like or the one that there were 2 ways I showed you.
And for number 5, you have to do long.
Yeah, long division first here. Yeah. And then you go and do the rest. This last, hey, wait a minute. That's the problem I just gave you, no? With different limits of integration. That's 6 question review? Are you kidding me? Okay, let me see if I have another one. Now this is for my internet students. I can show you that. Let me see. It's going to be slightly different, but theirs covers a little bit more material because it's the first time I've met them in person or well on Zoom. So basic, just split it into 3 fractions and then use power rule. Basic U sub, right? See it, x to the 5th plus 4, take derivative of that, and that's that. This one, basic U sub, U is 1 over x, the derivative of that is here. Interesting one right here. What's that? By parts twice. It'll take 2 times to get that to work. Oh, hey, that looks familiar. Linear over quadratic. Partial fractions with the long division there, right? Hey, I started class with this problem, but I'm only going from negative infinity to 2. So this one does converge. And then this one right here. What's the issue with number 15?
1.
You have a problem at 1 and you're integrating from 0 to 9. So that's like the problem we just did where you have to split it into 2. No. So, I mean, you can go back. I'll post this video later. You can go back and look at these if you want. I actually have solutions there. Let me see. Let me see what if I have any old exams. What does some old exams look like? I always make my exams brand new, so it doesn't matter. How far do we want to go back? Let's look at a 2015 one. I wonder. Here's a 2015. Now this is probably, I don't know what we're covering here because every class is a little different, like where we stop at the first exam and start the second one. That's basic U sub. It doesn't look like it, but it is. Parts. Definite integral. You have a problem at 0, right? Natural log of 0. Oh shit. So this is an improper integral that requires integration by parts. Sketching a curve. Okay, we haven't gotten to that. Find the volume of the solid. Okay, we haven't done any of that. So they were at a way different place. All right, it's 10:40. 10:40, so we'll call it. Tricky part's making an exam that you can finish in 1 hour and 40 minutes, right? All right, everyone. Have a great day. Any questions at home? We're gonna shut it down.
That should do.
Okay, y'all have a good one.